What if everything you see, everything you are, isn't made of tiny, point-like particles, but of unimaginably small, vibrating strands of energy? What if the universe, in its most fundamental essence, is playing a grand, cosmic symphony, and we've only just begun to discern the melody? Welcome to the Cosmic Question, where we dive deep into the biggest mysteries of the universe. Today, we're unraveling one of the most ambitious, elegant, and profoundly controversial ideas in modern physics: string theory. Is it the long-sought key to understanding the very fabric of reality, a theory of everything? Or is it a beautiful, intricate mathematical tapestry leading us down a fascinating but ultimately unproductive cosmic dead end? Let's decode it. The fundamental problem: uniting two giants. To truly appreciate why string theory was proposed, and why it continues to captivate so many brilliant minds, we must first understand the monumental chasm it attempts to bridge. For a century, physics has rested on two colossal pillars. First, there's general relativity, Einstein's revolutionary theory of gravity, which describes the universe on the grandest scales: the dance of planets, the birth and death of stars, the expansion of galaxies, and the curvature of spacetime itself. It's a theory of stunning accuracy and profound beauty when dealing with the large and the massive. Then we have quantum mechanics, the equally revolutionary theory that governs the realm of the infinitesimally small. It describes the bizarre, probabilistic world of atoms, electrons, quarks, and all the other fundamental particles that make up matter, and the forces that govern their interactions, excluding gravity. Quantum mechanics has been spectacularly successful, forming the bedrock of our modern technological world, from lasers to computers to medical imaging. Both theories are triumphs of human intellect, verified by countless experiments within their respective domains. But here's the crux: when you try to make them work together, when you attempt to describe situations where both extreme gravity and quantum effects are crucial, such as the singularity at the heart of a black hole, or the universe in the very first fractions of a second after the Big Bang, the mathematics falls apart. The equations spit out nonsensical infinities, signaling a fundamental incompatibility. For decades, physicists have dreamed of a single, unified framework, a theory of everything, that could seamlessly weave gravity and quantum mechanics together. Enter string theory, the basic idea. Enter string theory. Emerging from initial ideas in the late 1960s and blossoming through the 1970s and 80s, it proposed a radical departure from the then-standard view of particles as zero-dimensional points. What if, string theorists asked, the ultimate constituents of all matter and all forces are not points, but tiny, one-dimensional vibrating strings of energy? Some of these strings are open, like tiny segments, while others are closed loops. Think of a violin string. By vibrating in different modes, at different frequencies, a single string can produce a rich variety of distinct musical notes. String theory postulates something analogous for the universe. These fundamental cosmic strings can also vibrate in an infinite number of different patterns. Each unique vibrational mode, each distinct note in this cosmic symphony, manifests itself to us as a different kind of fundamental particle. An electron is one pattern of vibration. A photon, the particle of light, is another. A quark is yet another. All the diverse particles we observe in nature are, in this view, merely different resonant frequencies of these underlying strings. This is an incredibly alluring prospect, a universe built not from a bewildering zoo of disparate particles, but from a single, fundamental entity, elegantly simplifying the building blocks of reality. Extra dimensions and compactification. Now, here's where the theory takes an even more mind-bending turn, requiring a conceptual leap beyond our everyday experience. For the mathematics of string theory to be consistent, for it to work without generating those problematic infinities that plague other approaches to quantum gravity, it demands the existence of more spatial dimensions than the three we perceive: length, width, height. Most consistent versions of superstring theory, a more developed version incorporating a symmetry called supersymmetry, predict a universe with a total of 10 spacetime dimensions, 9 spatial dimensions and 1 time dimension. M-theory, an even more encompassing framework that attempts to unify different string theories, suggests 11 spacetime dimensions. So if these extra dimensions exist, where are they? Why don't we see them? The prevailing idea is that these additional spatial dimensions are compactified, meaning they are curled up or rolled up on an incredibly small scale, far, far smaller than an atom, perhaps as tiny as the Planck length, which is about 10 to the minus 35 meters. Imagine a tightrope walker on a wire. From a distance, the wire appears as a one-dimensional line. But for an ant walking on that same wire, it has a clear second dimension, the circumference of the wire. Similarly, these extra dimensions in string theory are thought to be curled up into complex, multi-dimensional geometric shapes, often referred to as Calabi-Yau manifolds. These aren't just simple circles, they are incredibly intricate structures, and the precise way they are folded, twisted, and interconnected would be crucial. The promise, a theory of everything. The geometry of these hidden, compactified dimensions would dictate the allowed vibrational patterns of the strings. And since these vibrations determine the properties of particles, their masses, their charges, the strengths of the forces between them, the shape of these extra dimensions would essentially define the fundamental laws and constants of our specific universe. One of the most exciting early indications that string theory might be on the right track was that its mathematics naturally predicted a particle with precisely the properties expected for the graviton, the hypothetical quantum carrier of the gravitational force. This was a huge breakthrough, as previous attempts to incorporate gravity into quantum field theory had been consistently thwarted by uncontrollable infinities. String theory, by replacing point particles with extended strings, seemed to smooth out these infinities, offering a finite theory of quantum gravity. This led to the grand promise. If string theory is correct, it could be the ultimate unified theory, describing all fundamental particles and all 4 fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces, as different manifestations of these vibrating strings. It held the potential to explain why the universe has the specific properties it does, deriving them from first principles. It was, and for many still is, the holy grail of theoretical physics. The challenges: why the skepticism? So if string theory offers such an elegant and powerful vision, why isn't it universally accepted as the final answer? Why do some prominent physicists express skepticism, even suggesting it might be a cosmic dead end? The reasons are significant and have fueled decades of intense debate. Challenge 1: lack of experimental evidence. The most formidable challenge, and the one most often cited by critics, is the lack of direct experimental evidence. Science, at its core, is an empirical endeavor. Theories, no matter how beautiful or mathematically compelling, must ultimately make testable predictions that can be verified or falsified by experiment. String theory operates at energy scales and length scales that are almost unimaginably extreme. The strings themselves are theorized to be on the order of the Planck length, vastly smaller than anything we can probe with our current technology. The energies required to see direct evidence of strings, or the effects of these extra dimensions, are many orders of magnitude beyond what even our most powerful particle accelerators, like the Large Hadron Collider at CERN, can achieve, energies perhaps only present in the earliest, fiercest moments of the Big Bang. Without experimental confirmation, string theory, for now, remains a highly developed mathematical framework rather than a physically proven theory. Critics argue that a theory that cannot, even in principle for the foreseeable future, be tested, risks straying from the realm of empirical science into pure mathematics or even philosophy. Challenge 2: mathematical complexity and the landscape problem. A second major hurdle is the profound mathematical complexity and the landscape problem. String theory isn't a single, uniquely defined theory. It's more of a framework, encompassing various related models, such as the 5 distinct superstring theories that were later shown to be different aspects of a more fundamental, yet still mysterious, M theory. The mathematics involved is exceptionally sophisticated and challenging. Furthermore, it appears that there isn't just one way to compactify those extra dimensions. Instead, the theory seems to allow for an astronomical number of possible solutions, perhaps 10 to the power of 500 or even more, each corresponding to a different way the extra dimensions could be curled up. Each of these solutions, or vacua, would describe a universe with potentially different physical laws, different fundamental constants, and different types of particles. This vast array of possibilities is known as the string theory landscape. If the theory permits such an enormous number of potential universes, how do we find the one that describes our own? And if the theory is so flexible that it can accommodate almost any set of physical parameters, does it truly predict anything specific about our universe? This landscape has led some to invoke the Anthropic principle, the idea that we observe our particular universe with its specific laws and constants, because these are the conditions necessary for life like ours to exist. In a vast multiverse of possibilities, perhaps only a tiny fraction can support complexity. But for many physicists, this is an unsatisfying explanation, feeling more like a philosophical retreat than a predictive scientific statement. Challenge 3. The question of supersymmetry, SUSY. A third challenge relates to a concept called supersymmetry, or SUSY. Most consistent and promising versions of string theory require supersymmetry. This principle postulates that every known fundamental particle has a corresponding superpartner particle with slightly different properties, specifically a different quantum spin. For example, the electron would have a superpartner called the selectron, quarks would have squarks, and photons would have photinos. Physicists had high hopes that these superpartner particles, if they exist, would be discovered at the Large Hadron Collider. Their existence could solve other theoretical puzzles beyond string theory, like the hierarchy problem, and some superpartners are good candidates for dark matter. However, despite extensive searches, no evidence for supersymmetry has yet been found at the energies probed so far. While this doesn't definitively rule out string theory, supersymmetry could exist at higher energies than currently accessible. The persistent absence of experimental support for SUSY is a significant disappointment and weakens the case for many popular string theory models. The ongoing quest and alternative theories. Despite these profound challenges, string theory is far from abandoned. Thousands of brilliant physicists around the world continue to dedicate their careers to it. Why? Because the allure of its potential unifying power remains immense. It has also, undeniably, led to profound and unexpected breakthroughs in pure mathematics, forging new connections between seemingly disparate mathematical fields. Some proponents argue that the current lack of experimental evidence is a reflection of our technological limitations, not necessarily a fundamental flaw in the theory itself. They believe that, eventually, indirect evidence might emerge, or new theoretical insights will pave the way for testable predictions. It's also important to note that the quest for quantum gravity is not solely reliant on string theory. There are alternative approaches. Loop quantum gravity, for instance, attempts to quantize spacetime itself, building it up from discrete loops or quanta of space, without requiring extra dimensions or supersymmetry. Other ideas include causal dynamical triangulations, asymptotic safety, and theories based on emergent gravity. Each of these alternatives has its own set of strengths, weaknesses, and dedicated researchers, and none have yet achieved the status of a fully validated theory of everything. Conclusion: Symphony, dead end, or stepping stone. So, string theory, universe's hidden symphony or cosmic dead end. The jury is still very much out. It remains a monumental work in progress, a grand intellectual adventure that has pushed the boundaries of human imagination and mathematical prowess. It has provided us with a new and powerful language to ask incredibly deep questions about the ultimate nature of reality, space, time, and matter. Perhaps in the future, new experimental discoveries or unforeseen mathematical breakthroughs will vindicate its core tenets. Perhaps indirect cosmological observations, like subtle imprints on the cosmic microwave background, could provide the first hints of its validity. Or perhaps string theory will ultimately be recognized not as the final theory itself, but as an essential stepping stone, a crucial part of the scaffolding from which an even more profound and complete understanding of the universe will one day be built. Its impact on theoretical physics and mathematics, regardless of its ultimate fate as a theory of our specific universe, is already indelible. The quest to understand the universe at its most fundamental level is one of humanity's oldest, deepest, and most noble aspirations. String theory, with all its complexities, its beauty, and its frustrations, represents a colossal and ongoing effort in that grand quest. What are your thoughts on this enigmatic theory? Is the sheer mathematical elegance and unifying potential of string theory enough to maintain faith in its pursuit, despite the formidable experimental hurdles? Or do the persistent lack of evidence and the challenges like the landscape problem signal that it's time to more vigorously explore alternative paths to quantum gravity? Thank you for joining us on The Cosmic Question as we've journeyed through the intricate world of string theory. We encourage you to continue asking, continue learning, and continue to marvel at the magnificent, mysterious universe we are all a part of. Until next time, keep questioning.